Hi there, this is video 28. This is a good news, bad news video. Good news, it's the second to last video in this class. Bad news, it's probably going to be a little long. So this is chapter 6, section 5. And this is all about graphing rational functions. And asymptotes. So let me just give you a really quick clue before we go on and do anything. If you have, let's say, here's your XY, because we haven't done any graphing in this class. So this is the only real section where you're going to graph anything. First off, rational function. We solved these earlier. Rational means fractional. So you're going to have some fractional function where you're going to have f of x equals some polynomial over a polynomial. And when that happens, you have asymptotes where these functions often look like curved lines somewhere on the graph. And then there's these asymptotes. Well, I didn't draw that very well. Let me go backwards. So I'll actually put them in these quadrants. And then there's these asymptotes, which are dotted lines. And in this case, I'm just going to use the actual axes themselves. So the asymptotes are lines asymptotes. These are dotted lines. And depending, if you have a graphing calculator, you're not going to actually see the dotted line. So, nor would you in Desmos. So, dotted lines drawn on a graph. So, they're also imaginary on a graphing calculator. That a graph will approach but not touch. Okay, so you draw them in as dotted lines because they're not actually the graph. Your graph here, I drew the graph in red, are solid lines. These rational functions always have two parts to them, a top and a bottom, often in opposite diagonal quadrants of the graph. And so you need to be able to tell where the function's going to go and where the asymptotes are going to go. So I'm going to give you 7 different steps. We're going to write all of them out first, and then we're going to follow those steps and plot a couple of functions. So we'll do that, and then I'll probably try to put them on 2 screens while we do that. So let's go from here. Let me add some. All right, so here is step 1. Well, not even a step yet. Let f of x, let some function, and in the text it looks like this, n of x over d of x. So this is a numerator, n of x over a denominator, d of x, where n of x and d of x are polynomials. Okay, so not just a constant, they're actually polynomials. So, step 1, simplify. That means factor. Both of them if possible. And I'll change pen colors between these just so that they stand out a little bit and skip a line. 2, find and plot the y-intercept. If there is one. And here's how you're going to do that. By evaluating f of 0 in the simplified function. And we're going to write out all these steps, and then we'll actually do it for an actual problem. Okay, so you're going to simplify, then you're going to plug 0 in for x, and that's going to give you your y-intercept. Then you're going to plot it. So that's step 2. Okay, and then step 3, skip a line. Find the zeros of the numerator. Zeros of the numerator. Remember, that's n of x. If there are any. By setting the numerator equal to 0. Plot any corresponding x-intercepts. Okay, so we'll take care of that. Next, step 4, find the zeros of the denominator, d of x. If there are any. By setting the denominator equal to 0. Sketch the corresponding vertical asymptotes. I spelled corresponding wrong up here. Corresponding vertical asymptotes. That means they go up and down. As dashed or dotted lines. I'm going to put dashed. You can put dotted, whichever you think you're going to do. And plot any holes. We'll talk about those using open circles. So here's a little note. Oh, this is actually 5. Okay. Note, the holes come from setting any canceled quantities. From step 1. So when you simplify and factor, if you have any factors, top and bottom, that cancel out, you're not going to use those in this, like steps 2, 3, and 4. But if they cancel out, you're going to set that canceled quantity equal to 0, and that's going to become a hole from step 1. So setting any canceled quantities from step 1 equal to 0 and solve. And I believe in the example that I have, we are going to have a hole in the graph. So we'll see that happen. Okay. I should have skipped a step between 5 and 6 there, or 4 and 5. All right. So 6. All right. The graph f of x so this talks about horizontal asymptotes, has at least one horizontal asymptote and it is determined by comparing the degrees of n of x and d of x. And here is how that happens. So one of 3 things is going to happen. Either A, oh boy, I didn't write enough information in my notes. Okay. 2 and 2, n is equal to m. Okay, I am going to, so here's some information that I have, but I didn't write enough info. I may have to go grab a book and I can't pause this, so you might have to just kind of pause and keep on going. So let's see, this says if n is less than m, and I'm unsure which one's n and which one's m. All right, well, if n is less than m, then the horizontal, then y equals 0 is a horizontal asymptote. And so that is y equals 0. So that's the x-axis. So that would sit right on the x-axis. All right, I'm going to go snag my pre-calc book really quick so we can figure out something. Be right back. Alrighty, so let me take a quick look in here. I don't remember which chapter this is in here. It's pretty early on in this book. Polynomial functions. Let's see. Graphs of rational functions. 156. Okay, so n is coming from the degree of your numerator. All right. So we have a little side note here. N is the degree of the numerator, and m is the degree of the denominator. That's an important piece of information. So you need to have that in order to adhere to all these rules. Okay. So the first one was if n is less than m. And then the next one, b, if they're equal to each other, then y equals a over b is a horizontal asymptote. Where a is the coefficient on n of x and b is the coefficient on d of x. So you're just taking the leading coefficient, I guess I should add to both of those. And we'll, again, see this when we do this. And then c is, and I'm not going to give you any of these, and I'll tell you why. If n is greater than m, then there is something called a slant asymptote. At the quotient of the numerator divided by the denominator. And this requires long division, which is why I'm not going to be doing this. Okay, so you won't see any problems like that. So you should know that that can happen, but it won't happen in the problems that you guys are going to have. All right, and then I have a little note in my notes to recall that the domain of a function comes from setting the denominator equal to 0 and solving for what x cannot be. All right, and then there's a number 7. Plot at least one point that's a p, point between and 1 point beyond at least 1 point between and 1 point beyond each x-intercept and vertical asymptote. So that you know what it's doing and can figure that out. All right, so let's go do a problem. All right, what I'm going to do is I'm going to go view, dual page, turn that on, and we're going to go there. And on that page, we're going to throw some. All right, so here is the problem we are going to do. Here's an example. Sketch f of x equals x squared minus 9 over x squared minus 2x minus 3. All right, so step 1, and I'll try to follow along in colors here, says factor both numerator and denominator if possible. So my numerator here is x squared minus 9, which is a difference of squares. So that's going to be x plus 3, x minus 3. And my denominator is a trinomial, 3 terms. You should think x method. And so I have a minus 3, minus 2. My side factors there are going to be a 3 and a 1. I need a negative and a positive. So those are going to be x minus 3, x plus 1. Excuse me. And then you know from all the work you did back in the rational functions that if you have a common quantity that can be canceled out, you're going to cancel those out. And the simplified function is actually going to be x plus 3 over x plus 1. Okay, so that's what we've got for now. Now, step 2. Find and plot the y-intercept by evaluating f of 0. So I'm going to do f of 0 of x plus 3 over x plus 1. I'm taking this simplified version to do that. So it means I'm going to put 0 where x is. So I have 0 plus 3 over 0 plus 1. And that's going to give me 3. So that means a y-intercept. Now remember, this is my x value, right? X equals 0. So I now have an ordered pair, 0, comma 3. And we said we're going to plot. So I'm going to go grab one more. And my content, let me go up here. All right, so what we're going to do here as we go is just kind of plot some information. Whoops. Let me erase that. I want to move this guy and make him a little bit bigger. Okay, so back to a pen. I'm going to plot in purple my 0, 3. That's my y-intercept. So I know my graph is going to hit that when I go. Okay, so I'm going to go back to the screen. Red. Step 3. Find the zeros of the numerator by setting the numerator, x plus 3 equal to 0. And plot any corresponding x-intercepts. Okay, so I have an x equals negative 3. So I'm going to go back to my graph and plot that as an x-intercept. Now, that means I have the point negative 3 comma 0 if that's an x-intercept. So I'm going to go over here, negative 3, 0, x-intercept. Okay, back. Number 4 is kind of this yellowy color, orangey color. Find the zeros of the denominator by setting the denominator equal to 0, which is x plus 1 equals 0, which means x equals negative 1. Actually, I'm going to... Oh, that was weird. Okay, so I'm going to go, so x equals negative 1. And this says, going back to the step over here, sketch the corresponding vertical asymptote. So I have a vertical line on my graph at x equals minus 1. Okay, so back to the graph. Here's x equals negative 1. So I'm going to have a vertical line here at x equals minus 1. You should put arrows on that asymptote. It goes forever and ever and ever up and down that graph, but it is dotted. So remember, I said these graphs are always split into 2 parts, right? You can see that there's 2 dots now on either side of that asymptote. Let's go back. Holes in the graph, number 5, green. The holes come from setting up any canceled quantities. Now, we did cancel these x minus 3s were canceled way back at the beginning. So it says take any canceled quantities from step 1, and we get x equals 3. Now, what you do with that, I didn't really explain this part, is we now plug this value into the simplified equation from step 1 to find the y value. Okay, so I need to find basically f of 3 into x plus 3 over x plus 1. So this gives me 3 plus 3 over 3 plus 1 is 6 over 4 is 3 over 2. So I now have the point 3 comma 3 over 2, which is 1 and 1/2. So that's a hole in my graph. So 3 comma 1 and 1/2. Okay, so 3, 1 and 1/2. So I have a hole here. That means my graph is not going to hit that, but it's going to kind of go to it and then skip over it. Okay, now let's go to number 6. Number 6 is pink. Graph of f of x, so here's where our horizontal comes into play. Now we're looking at the degrees of the numerator and denominator. So skipping back to this screen, degrees of our original numerator and denominator. Well, even if not, degrees of this guy, they're both 1s. So they're equal to each other. Okay, so we are looking at, in this one, b, n is going to equal m. So in this one, n equals m. So that means we have a horizontal asymptote at y equals a over b, which in this case means the coefficients of those are 1. So y equals 1 is a horizontal asymptote. Okay, so let's go plot that. Now that's going to be a dotted or dashed line also. So we're going to go draw that in. Y equals 1. Now you may not have all these colors when you do yours, but same basic idea when you do. All right. Let's go back to the last part. Now, let's skip over here, bring this down. All right, number 7. And I'm going to have to extend my page here quite a bit. For number 7, it says, plot at least 1 point between and 1 point beyond each x-intercept and vertical asymptote. So what that means is if I go back to my graph, I need to know what's happening on either side of this x equals -3, my red dot here. And so I'm going to see what happens at x equals -4 and -2. Okay, so we're going to make an XY table. You're going to make an XY table. So I'm going to X, Y, and I know I'm going to check -4 and -2. Now I'm going to go back. Now that takes care of the left-hand side of my graph. Now, again, if I look over here, 1 point between and 1 point beyond each x-intercept and vertical asymptote. So let's go back to the graph. Now I have a vertical asymptote here. I don't have any x-intercepts over here, but I need to know kind of what's happening. You can kind of picture what's going to happen. I know it's going to raise up from here and come close to this intercept. And it's going to, you want to know what's going to happen on either side of this hole. So maybe check like 5 and 1. just so that you have an idea of what's happening there. You should probably also check -1/2 just to see, so you know what's happening between the y-intercept and that asymptote. So for sure, -1/2, 1, and 5 will do. -1/2, 1, and 5. So we're going to do -1/2, +1, and 5. And the function we're testing into is x plus 3 over x plus 1. Right? We're just going to plug an x value in, see what the y is. All right. So if we do that, I'll do these with different colors. So I'm going to plug in -4. -4 plus 3. Oh, that didn't even. -4 plus 1 is -4. This is a -1 over -3 is a positive 1/3. Okay. And then I'm going to put a -2 in there. Different color. -2 plus 3 over -2 plus 1 gives me a 1 over a -1 is a -1. Okay, so let's go plot those. -4, positive 1/3. -4, positive 1/3. So that's right there. And then -2, -1. So that's right here. So it's easy enough to see that this guy is going to come close to this asymptote, hit these couple points, and then it's going to drop down and come close to this asymptote. Okay, that's what's going to happen on the left-hand side of that graph. Let's see what happens on the right-hand side. Back down to my table. Okay, excuse me. I'll do the whole numbers first because they're just simpler. So I'll do the 5. 5 plus 3 over 5 plus 1 is 8 over 6 is 4 over 3. So 4/3. Then I'll put a 1 in. 1 plus 3 over 1 plus 1 is 4 over 2 is 2. Okay, so let's go put those in. 1 comma 2 and 5 comma 4/3. That's 1 and 1/3, by the way, right? So 1 comma 2 and 5, 1, 2, and 5, 1 and 1/3. So that's just a little bit above that line. So this is enough of an idea here that you can see the curve, but we'll verify it with the, so what's going to happen here is this is going to come down to here and then come through and just keep on going. Now we'll do that half just to A, do the math, and B, verify what's happening. All right. So let me just erase some of these things here. Let's get rid of this. Get rid of this. Get rid of this. Okay, so in this space over here, we'll do this guy. So we have -1/2. So we have -1/2 plus 3. Oh, Lord. Come on. -1/2 plus 3 over -1/2 plus 1. Well, -1/2 plus 3, this would be 6/2, is 5/2. This would be 2/2. This would be 1/2. And then keep, change, flip, you would, this is actually 5, which is crazy bizarre. But that's what that works out to. So -1/2, 5. -1/2 up to 5. So this guy is going to finish this graph by doing that. Okay, so that is what that graph looks like by going all the way through these steps. Now for you guys, I have graph paper in my room. I would highly advise, do not draw these out and try to graph them on your own. I do not, because you guys won't like, here's what I'm saying. You're not going to draw exactly perfect squares, and these things are going to look like a hot mess. make sure your asymptotes are dotted, and blah, 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 blah. So also, you should know that if you try to do these in Desmos, it's not going to show holes. It's not going to show asymptotes. So while you can sort of see these in Desmos, you can't exactly see the entire graph. So just an FYI. I think this is the only one that I did because I didn't want these notes to be super, super long. And that's enough to give you an idea. But you will need all of these rules. Okay, so you're going to need to see that whole page of rules when you do these. All right, good luck. We're almost done. We're at the end. Toodaloo.